In this video, let's take a look at some more operational transforms. So the first one we're going to consider is time differentiation. So we want to say, what is the Laplace transform if we take the derivative of f of t with respect to t? And so it turns out that is equal to s times capital F of s minus lowercase f of 0 minus. So very important to note that this is our lowercase f, so this is the value in the time domain at t equals 0. So value of our function in the time domain at t equals 0 minus, so our initial value of that function. And so we can say, well, what if we keep taking more and more derivatives? So let's look at our second derivative and then let's generalize it from there. So if we have a second derivative of f of t with respect to t twice, what we have then is s squared times capital F of s minus s times lowercase f of 0 minus. So again, this lowercase f indicates our time domain, and then minus df 0 minus dt. So we're taking the derivative of our time domain function and then evaluating that derivative at 0 minus. So again, keep in mind that both of these are time domain, lowercase f. Okay, so let's generalize that though. So let's say we want the Laplace transform of the nth derivative of f of t, so that's with respect to t in times. And so if we generalize, we can then have that this is s to the power of n times our capital F of s. And so I should state, if it's not clear, that of course this capital F of s is just the Laplace transform of our f of t. So we have s to the n of this f of s minus s to the power of n minus 1 times lowercase f of 0 minus, so our time domain function evaluated at 0 minus, minus s to the power of n minus 2 times the derivative of f with respect to t evaluated at 0 minus, again this is our time domain, minus s to the n minus 3 times our second derivative of f 0 minus. So we're taking the derivative of our time domain function twice and then evaluating that at 0 minus, minus so on and so forth until eventually we're going to get to a term that does not have an s, and we're just going to have the n minus 1 derivative of our time domain function f with respect to t to minus n evaluated at 0 minus. So that would be our generalized function. In this class, we're rarely, if ever, going to go beyond the second derivative, but I think it's good to understand how to use these general functions as well. So that was our time differentiation. What if we want to do time integration? Okay, so for time integration, we're saying we want the Laplace transform of the integral from 0 to t of f of x dx. And so here I basically just am using x as a dummy variable. We can see when we evaluate that limit of t, our t is coming back in. And so it turns out that this is equal to f of s divided by s. So in general, then we can kind of see that this integration in time leads to dividing by s in frequency, whereas in general for this first order case up here, we can see that differentiating in time corresponds to multiplying by s in frequency, and we also get this minus our lowercase f of 0. Okay, so that was a lot easier, time integration. So we've looked at time differentiation, time integration. Now let's look at frequency differentiation. So frequency differentiation. And so sort of we're going to see the result first, but basically what this corresponds to, well actually let's write it this way. So we're saying if we have negative dfs ds And so I've just included the negative sign here to be consistent with your book, but basically if we take the derivative in frequency, that's going to correspond to multiplying by t in the time domain. So we have Laplace transform of t times f of t is equal to negative df of s with respect to s. So deriving in the time domain, or deriving in frequency, corresponds to multiplying by t in time. And so that kind of checks out because up here for our time differentiation, we saw that differentiating in time, we had this multiplication by s in frequency. So we see sort of a similar operation. So now I'm going to write a more generalized function, and so this is not in your textbook, so this might be useful to know. So we have the Laplace transform of negative 1 to the power of n, t to the power of n, f of t is equal to the nth derivative of f of s with respect to s in times. So again, this is a more generalized one, which is not in the book. I believe they have it for the second derivative, but they don't generalize it. So again, this we can see makes it a lot easier to deal with if we have our second, third, fourth, and so on derivative in our frequency domain. So the last one that I want to look at is time periodicity. So time periodicity. So we've already looked at, for instance, how to deal with our sine wave, and so of course that's a periodic function. But what if we have something periodic that's not a sine wave? So maybe it's a triangle wave, a square wave, or maybe something a lot more complicated that, you know, it's repeating. So how do we deal with that? Because we don't necessarily want to be integrating forever over infinity, because remember our definition integral goes from 0 minus to infinity. So let's say this is some periodic function with a period t. And so basically what that means is if we write it, we could say f of t is equal to f of t plus n times capital T, the period, for n equals 0, 1, 2, and so on. So basically that's saying we're just repeating every time we increment by a period in time. And so it turns out that in that case, if this is our f of t definition, that our Laplace transform of this f of t, which is our periodic signal defined above, is equal to our f of s, which is f1 of s, divided by 1 minus e to the minus capital T s. So the capital T is our period. And so this f1 of s in the numerator is the Laplace transform of that first period. So this is our Laplace transform of f of t on the first period. So basically what this is saying is we don't have to worry about trying to integrate this function over infinity, but we can just focus on the first period and then we divide it by this term here. So again, this can become very difficult to keep track of all of these different operational transforms that we've looked at in this video and the previous one. So ultimately what we're going to do is just use a table. So we have a table for common transform pairs, and we also have a table for common operational transforms. And so this is also on Canvas, and you can see it as well on page 685 in the textbook. Even with these tables, I don't want you to get complacent and think it's very easy to do. I have all the sort of transform pairs and operational transforms, because it can still be pretty difficult. So make sure you take the time to get familiar with how to use these two tables.